the computer and whatnot, so I think we can go ahead and get this last lecture in bridge engineering started, right? I mean, I can see you all are having a hard time containing your sadness over the whole thing, right? It's a joke, not a very funny one, right? You're ready for it to be over? No, I do understand that these, one night a week marathon sessions in bridge engineering can be kind of rough, but I think we've gotten through some pretty good material, and I think the class has come together pretty well. Let me start off with the pedigree info. I'll get the sign-in sheet passed around. Let's talk a little bit about housekeeping, just so everybody's clear on where we're at in terms of the grade. So I posted the grades to your research presentation. All in all, everybody did well. I took a couple notes during everybody's presentation just to try and come up with a rubric for how to assess everybody, but all in all, the grades were all pretty closely lumped together and everybody did fine, so no real issues there. Okay, so your homework 4, I'm just going to be completely frank, I've been swamped and haven't had time to fully go through and grade it. I got a fair amount of it done, but not as much as I would like. But my goal is to try and post those grades sometime in the next couple days. You all have a design project, and hopefully the lecture tonight kind of ties everything together, which leads to the final. Okay? The final in this class is really just, it's a lot of short answer and conceptual stuff. I don't do calculations on this final because you all are going through them right now like crazy. In other words, there's really nothing for me to test you on computationally since you're doing everything right now for the project. I mean, your computations required for the project is everything we've covered in the class, so there's nothing left for me to test you on. What, am I going to make you do it again? That's the whole point of the project, is for you to build one massive spreadsheet that'll do everything for you. If I give you another problem, you just flip the numbers in, and there you go. So it's just going to be short answer stuff. I'll email that out probably sometime in the next couple days. We'll keep it simple. Do the same time your project is, Friday of finals week. I can grade that pretty quickly. Sound good? What would we say, 5 p.m.? I'm pretty easy to get along with. Sound good? Any questions? All right. Tonight, I know I said we have one final topic, which is deck casting, and that is, in fact, true. Let me move this over so I can sort of shut this. I had to plug my mic up down here because the USB port is not going along with me. All right. I know I said we were going to talk about deck casting tonight, and we are, but I think what can happen in bridge engineering is there's a lot of stuff going on. There's fatigue, and there's service 2, and then there's plastic moments, and DC1, and all this, and it's kind of hard to tie everything and bring it all together into one cohesive picture. Hey, here it is. So what I've decided to do is this. I'm going to show you a short presentation on some research that myself and a couple other faculty did. One of them's at WVU and one of them's at the University of Wyoming. The 3 of us tend to do a fair amount of research together, and I'm going to show you a short little presentation that we did, some research on deck casting to kind of explain what's going on and what are the issues, and then I'm going to go through a full-blown start-to-finish bridge design example, okay, so that you can kind of see it all in one big coalescent picture. And there it is, okay, because I know that with this class, you come in one week and I teach you how to do section properties, okay. And you come in another week, okay, here's DC1, DC2, okay. And then now let's put it all together. And that, I think, putting it all together, sometimes it's kind of hard to see that big picture. And that's kind of what I want to show you tonight, all right. Sound good? All right. So let me talk a little bit about deck casting. And I'm using this, I'll be honest, it might seem like I'm being a little lazy because I'm using a previous presentation that I generated, but I think it's kind of important because the presentation really does hit the nail on the head for our last topic, which is constructibility. So a little bit of background so that you all have an understanding of what's going on. like I said, I do a lot of research with my research group at WVU here and University of Wyoming. And one of the things that we developed and have been really sort of pushing its advertisement among the bridge industry is an online design tool called eSpan 140. And I mean, I'm sitting here telling you this, and I know full well that you could probably go on to eSpan 140 right now and come up with a trial size for your design project. And I'm totally fine with that. I don't have an issue with that, because really what I'm more interested in for your design project is that you're doing the math right, not that you got your initial size from rules of thumb or from eSpan. That's totally fine. But the idea behind the project was, if you go into the world of bridge engineering as it relates to concrete, pre-stressed and what have you, there are a lot of pre-made sections that are used very widely. How many of you have had pre-stressed or taken a course in pre-stressed? Okay, all right, so you have heard of like AASHTO type 1, type 2, type 3, all that. Those are pretty standard shapes that you see in pre-stressed concrete. Well, the concrete industry, they've had their stuff together because they've gotten their standardization down pat and developed for decades. In other words, they standardized their systems long ago, and they're AASHTO type 1, type 2, and all that. Those are the mainstay, and they have been for a long time and will continue to be so. Steel industry, not so much. I mean, within the world of bridge engineering, steel bridges are viewed like Swiss watches, that every steel bridge is its own unique snowflake. And that really doesn't need to be the case, because a 40-foot creek crossing doesn't need the same methodology applied to it that you would a 250-foot horizontally curved flyover. It's not the same story. So we've done a lot of work over the past few years to try and simplify steel bridge design, keep it as simple as possible, and that's where eSpan came into play. It's an online tool. You can literally go to eSpan140.com, create an account. Keep in mind, this is free. You can create an account. If you can create a Facebook, you can create an eSpan account. It's pretty simple. You go on, you input very simple parameters. How wide is the bridge? How long is the bridge? Does it have a sidewalk or not? What have you? And like that, it'll generate a design for you. Now that design it's a preliminary design, but it'll at least get you started. And the idea is that you can use it for cost comparisons to see whether or not for a given project is steel going to be the best alternative or is concrete. I mean, if concrete's the best alternative, go with it. But we wanted the options to be there. Well, in order to show that eSpan worked, we did a demonstration project out in Buchanan County, Iowa. I do a lot of work with county engineers, and the National Association of County Engineers, one of the higher-ups in the structures community there is the county engineer out in Buchanan County, Iowa. I have spent a lot of time in Iowa over the past couple years. I have seen enough corn to last me a lifetime. But they're good people out there. And we did a demonstration project on a 63-foot bridge out in Buchanan County. And us engineers, we like to double dip a little bit if we can. And while the bridge was being installed, one of the things that we were interested in was looking at deck casting. Okay. You're going to see here in a second, this whole semester we've been talking about the forces and the moments and the shears on bridges in their final state. When the bridge is done, here's the DC1, DC2. We've been treating the bridge as if it was finished, and here are the loads, here's the resistance, is it good? But that's not always the worst case scenario. Sometimes the worst case scenario is right then, when they're pouring the deck, because now it's just the steel shape by itself that has to resist all the weight of that wet concrete. And we wanted to do some research to see what's really going on. Do the assumptions that we make match the performance? Now, deck casting generates some pretty unique effects. So this is a picture that I took when I was standing on the creek side. And this is when they were getting ready to pour the deck. Now this silver part right here, that's the I-beam. They galvanized the beams for this project. So that's the actual I shape. Now you notice they've got these sort of steel brackets going along the beam. Those are overhang brackets. So they're using regular old stay-in-place formwork between the interior girders, but on the outside, when they want to form the overhang, they've got to extend it out a little bit, and that's where these overhang brackets come from. Now, problem is, on that exterior girder, you've got this load that's off to the side. It's going to want to twist that beam, right? Now, we make some pretty generic assumptions for how, oh goodness, we make some pretty generic assumptions for how the beam behaves in those situations. So if you dust off your structural analysis textbook whenever you took it as a junior or sophomore, what have you, you open the cover, okay, just open the cover, whether it's the front cover or back cover, I guarantee you, you are going to find these diagrams. Okay, these diagrams, if you don't recall, represent what are called fixed end moments. They're a pretty useful tool in structural engineering. We use them for things like moment distribution. I know if you took me for finite elements, I know you probably recognize some of these values because we use them for fixed end force vectors for beams. So they're pretty useful, and they show up sort of all over the place. Excuse me. So the idea is this: when we do a deck casting analysis and we want to generate or we want to determine that torsional effect, how much that girder is being twisted, we say that all the uniformly distributed loads, you know, like the wet concrete, we treat it like this, and we calculate that twisting moment as FL squared over 12, or the distributed load times L squared over 12, because that's the fixed end moment, okay? Any concentrated forces, concentrated force would be like that, the screeding machine, the bidwell. If you've ever been on a site where they're doing bridge casting, you can see the large screeding machine that they use to set the deck elevation. That we would treat as a point load, and we would just say that the bending moment is PL over 8. L being the distance between your cross frames. That gives you an idea of how much that girder is being twisted. Sound reasonable? Okay. So we did a number of analytical studies. I don't want to, you know, go nuts into the research. I mean, I'm not here to teach you about my research. I'm here to teach you about bridge engineering. A lot of the numerical studies and the stuff that's been done show that the equations that we use are pretty conservative. So that's really all you need to know. If you actually go through and do the modeling and the hardcore analysis, you'll find that these equations overpredict the amount of torsion in the girders. But that's fine for your perspective, because from your perspective, if it's overpredicting, then you're being conservative, and you can go home and sleep at night, sleep easy, because you know that the girder's fine. Make sense? Okay. So what we did is since all the studies were analytical in nature, we wanted to do some field testing. We wanted to actually collect some data and see what was going on. So we did this in October of 2013. You know, we checked the weather when we were heading out there, and it was supposed to be, you know, like 40, 50 degrees. Turns out it was 10. So I'm out there outside in the cold, wet, you know, 10-degree weather, and I literally was wearing everything in my suitcase all at once to try and stay warm. But yeah, it was still fun though. We went out and we instrumented the girders. We placed a lot of what are called strain indicators. The idea is as you load the girder deforms. These things will measure how much the girder is stretching or contracting at a particular point. You think if you got a strain there, you can get a stress and use basic mechanics to figure out your moments and all that. We did we looked at two different sections along the beam. So here's the beam, and it's going along the bridge. We looked here and here because those are the two sections that analysis showed to generate the worst bending or the worst torsional effect. So we figured let's just do the worst case scenario. We also did full-blown finite elements. So I know my finite element folks, you all should recognize this. How many are in finite elements now? Or anybody, is anybody in finite elements now? Are y'all doing stuff like this? this should be somewhat familiar, right? So, and I know you recognize stuff like this. So this is an image of the girder that was being analyzed. Now, let's just go back to basic mechanics, okay? Basic mechanics, I take a beam and I bend it like this. The top's in compression and the bottom's in tension. Make sense? Okay. So is anybody, if anybody's colorblind, and that has happened to me, I do apologize. This top portion of the beam is in blue, indicating that the stresses are negative, that they are in compression. The bottom beam is in red, indicating that they are in tension. That's what a stress contour looks like in finite elements. Usually, you'll have one color representing the extreme compressive stress and one color representing the extreme tensile stress. Sound good? Now, if all the girder was experiencing was just pure bending, then I would have a solid, blue color along the top. But notice how the colors kind of change. Like right here, it's kind of dark, and then it kind of gets a little lighter. Y'all see that? What's happening is that at that point, because it's funny how there's a cross frame right there, the girder's actually twisting a little bit. You're getting more stress on one side of the flange than you are the other. Okay, that's that torsional effect that we were trying to capture. When you go through and do all the stress squaring and do all this, you get two different stress effects in a particular girder. Now this one right here, this is your simply supported beam subjected to a uniformly distributed load. That's basically a moment diagram, and that should be pretty familiar. WL squared over 8, and then M over S to get your stresses. That's your regular old bending stress. This right here is the twisting effect. Now it's not, it's not as pronounced, but in some areas it could be. Now this is right here. That's what we're really getting. These purple lines here are indicating what the equations are predicting, these whole fixed end moment expressions. So they're predicting this, but dashed line here, that's what you're actually getting. So the long and short of it is, right here and here, which is where the cross frames are, they work very, very well, okay? But in the main body of the span, they're pretty conservative. Like you're actually getting a stress of about, like 800 psi, but the equation's giving you like 2400, so it's pretty conservative. We've been working on correction factors to try and take this and shift it down a little bit so that it actually matches what's really going on. The mechanics of it get a little funky, so it takes a little bit of thought to try and keep it simple. Does that make sense? Anybody have any questions on that? Okay. The only other issue that I think is relatively complicated is the idea of second-order effects. Now, a second-order effect can, I think, be most easily described as follows. So let's say that I'm standing on top of a hill, okay, and Barry decides he doesn't like me very much, and he decides to give me a shove, okay, so he shoves me. So if he shoves me, I might be able to catch myself and stand up. Now, imagine the same scenario, but imagine I'm wearing an 80-pound backpack. It's going to be a little harder for me to stand up, right? Now, here's why. As soon as he gives me a shove, okay, I'm standing like this, and I've got the backpack on. As soon as he gives me a shove, I'm like this, right? So now, here's me. That backpack is off-center, right? So there's an eccentricity. So basically, there's a bending moment, right? Now, what's that bending moment do? It causes me to move over more, which causes more moment, which causes me to move over more, which causes more moment. See how it sort of builds on itself? Okay? That's called a second-order effect. That's why you can imagine if you had a backpack on and somebody pushed you, you get that whoa, 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 whoa feeling. That's where that comes from. Does that make sense? Okay? You're going to see here in a second where we use this effect, which is called lateral flange bending. You're going to see where we use an amplification factor. That amplification factor is going to try and account for that second-order effect. Does that make sense? All right. Any questions on that? All right. If you understand that, then what I'm going to do is my sort of last presentation for you, which, by the way, I'm sitting here, I'm not doing my diligence. I do have handouts for all this stuff, I promise. Let me pass this out. There's that. There's that. that? There's that. Okay. My last presentation, if you will, is to try and take all of the math that we have done throughout this entire semester and bring it all together in one big, hey, here it is, PowerPoint. So, okay. So, like I said, I do a bunch of work with the steel industry. One of the organizations I do work with is what's called Steel Market Development Institute, which is where that whole SMDI thing comes from. Thank you. And we've done a lot of work to try and make bridge engineering, I guess, a little simpler, not just for students to grasp, but for professors to use. And we prepared a lot of lecture notes for engineers to use. So I figured, let's just save the best for last. So we prepared a start to finish, full-blown design example. Now, the way that I do bridge engineering, I think that this is a topic that is best reserved for the end, because if I were to show you this at the beginning, every single slide I'd be stopping and going, okay, let me explain what short-term and long-term is. Okay, now let me explain what DC1, DC2 is. Now you all understand all that, so I can actually go through the example and explain things in a logical fashion. Okay, sound good? All right, so let's talk a little bit about just the basics of the example. So I have some design notes. I'm designing this bridge according to ASHTO LRFD. This is a little bit of an earlier edition. We're using 5th edition. But honestly, for what we're doing, it's not really going to matter. A lot of this stuff doesn't change. So we're using 4 KSI concrete, 50 KSI steel. Do you remember we talked about this earlier on, that in LRFD, in the bridge spec, there are operational or importance, redundancy, and ductility factors, which are largely just placeholders in the spec. We're just going to take those to be 1. Now, the load combos that we're going to use, so we've got strength 1, we've got strength 4, which we haven't looked at yet, but strength 4 is going to show up for construction. That's going to be important for construction loads. We've got service 1 and service 2. Service 1 is really going to be our deflection check, and then we've got fatigue. Some additional values that I think are worth mentioning. We've got formwork, which we're taking to be 15 pounds per square foot, and a future wearing surface, which we're taking to be 25 pounds per square foot. These are values that I think we've referenced before in our other example, right? In example 1, when we were looking at DC1, DC2, we use these values. These are pretty realistic upper bound values, if you will. Okay? Now, here's the bridge. This bridge has a pretty wide girder spacing, but we wanted to accommodate two 12-foot traffic lanes and 2 5-foot shoulders, so it's a little bit wide. So we ended up going with 10-foot 6 girder spacing. The overhangs are just over 2.5 feet wide. We've got 2 jersey parapets on there that are about 15.25 inches wide. So this, I believe, should be some parameters that you all are fairly familiar with. Sound good? All right. Now, here's the girder, okay? This is the girder that's being checked. Now, you all, in a design setting, that's where Excel comes into play. You can just use your rules of thumb to make up some dimensions and then iterate until you get a final solution. Now, one thing you'll note is that this girder has 2 sections, like it has a flange transition right here. You all don't need to worry about that for your project. In other words, you know, you could take whatever girder you would use in the middle and just extend that across the board. I don't need you to trim the weight. What they're doing here is they're trying to trim a little bit of weight off the girder. In other words, you don't have as much bending moment right here, so you don't need as much flange. And if you can make the girder lighter, do so. If you can design one girder, you can design another. So I don't need you to go through and do all of that. Is that okay? Very good? All right. Okay. The dimensions from this girder came from eSpan. That's that website I mentioned earlier. You all can go to eSpan 140 if you want. I mean, I would check it out. And it's not because, I mean, I'm not saying that because, you know, oh, I was part of the research, so it's the most awesome thing ever, and you'd be crazy not to use it. That's not why I'm saying that. There was a lot of work that was done by a lot of folks other than me to help make eSpan a reality. And, you know, we got a lot of input from plate producers and fabricators and service centers, so it's really got a lot of good information put into it. One of the suggestions that came from the fabricators is for us to use nominal versus real values. The idea was if I want to cut a 16-inch flange, I have to use an acetylene torch. But if I actually measured, you know, a mark here and a mark here that was 16 inches and actually cut an acetylene, I'm going to burn a little bit off each end. So they suggested that for the design calcs, you know, like if we've got a 16-inch wide flange, let's use 15.75. Let's cut off a little bit. You don't have to worry about that for your project. That was just sort of a specific request from the fabricators in the room, so that's why we did it, because they know fabricating better than we do. So that's sort of where that came from. All right. So based on a given set of dimensions and a given girder, this is sort of the first step, right? So we've got the non-composite properties, the short-term composite properties, the long-term composite properties. Now we're looking at an exterior girder for this girder. Let me ask you, I'm just curious to see if you've been paying attention this semester. Why do you think that we're looking at an exterior girder versus an interior girder? Like, why would it make sense from a design standpoint if I'm going to look at one, why do I only look at the exterior? You can just guess. I mean, I'm just wondering. Well, no, that would be the difference between short-term and long-term. But I'm wondering, why are we focused on an exterior girder versus an interior girder? Well, you're talking about distribution factors, and you're exactly right. The live load distribution factors for the exterior girders tend to be larger, so they tend to see more moment. So if they're going to see more force, just design for those. Plus, the effective flange width. In other words, this effective flange width for this girder is shorter than it is for an interior one. So the girder itself is a little weaker. So in design scenarios, a lot of times engineers will just look at the exterior girders and just size them all the same. So if you wanted, you could design independent girders for the interior. I do believe for your project, though, you are looking at just an interior girder. And the reason why is because the lively distribution factors, I think, are a little easier to deal with. But it doesn't really matter. You could just plug and chug if you wanted. All right. So based on a given girder, you can compute this. And I've got to believe that by now you all can do this, right? You can compute all the necessary section properties, moments of inertia, centroids, all that stuff. You all should be masters at that by this point, right? Pretty basic stuff. Just plug and chug into your Excel sheet and go at it. All right. Any questions? Okay. Now, when you just make up a girder, you have to ensure that that girder meets cross, right? So in other words, we have to size a girder such that the web slenderness is less than 150. We have to size a girder such that the flange slenderness is less than or equal to 12, right? The web or the flange width must be greater than or equal to the web depth over 6, right? Flange thickness has to be greater than or equal to 1.1 times the web thickness. So, you know, given these girder properties, I can compute all the moments of inertia, but I better be using a girder that in fact makes sense, okay? Now, there's two more checks we need to make. This one should be fairly familiar, right? Because that's the one that guards against using a full-blown T-section, right? Like a supermassive compression flange and a really tiny tension flange. That's not an I-beam, that's a T-beam. That one's simple. This one's probably new. I haven't shown you this one, right? Okay. This one right here states that the width of the compression flange must be greater than or equal to L over 85. And let me indicate, for this, L equals the length of a field piece. So for instance, if you've got a girder that's coming out in 3 pieces, Each one of those pieces better meet this limit. The idea that the compression flange has to be wider than L over 85. That comes from the fabricators. I mean, the idea is this. If you have a girder and you set it down, you have a really, really tiny compression flange, the girder becomes really hard to handle. You know, it becomes really wobbly and it becomes pretty unstable. So you need a wide enough compression flange just to be able to pick the thing up and maneuver it, okay? So this doesn't really have anything to do with ensuring that the beam behaves like an I section. This is a constructibility check. You can tell because it's in 610.3, and 610.3 is the section on constructibility. So that's a new one, but that's just food for thought for real-life constructibility issues. Sound good? Okay. And each one of these checks you can see are good. You know, for instance, the web slenderness was calculated to be 63.5, and that's less than 150, which is good. So that's where the OKs come into play. All right. Next step then is to compute load. See, now I don't have to go back and explain, well, what the heck is DC1 and DC2? You all know what that is, right? So DC1 is the loads that are applied all to the non-composite section. DC2 are all the loads that are applied to the composite section. DW, future wearing surface and utilities, and then our live loads. Okay? So, here we go. We've got our slab, we've got our haunch, we've got that overhang taper on the ends for the overhang brackets, we've got the form work, we've got the girder weight, and then we've got all those miscellaneous details. So, here I'm just saying, oh, here's the loads, but we've gone through this, right? So you know how to compute girder weight and slab thickness and haunch weights. You all know how to do all that. We've gotten all that out of the way. So this should make sense. So we're getting a DC1 of about 1.23, something like that. And that's a pretty reasonable value. We've gotten stuff like that in here before. DC2, remember DC2, unless you've got utilities or something like that going on the bridge, the only really DC2 weight you're going to get is your barrier. And that comes out to be 0.153 kips per foot. Each barrier, these barriers are a little light. They're only about 300 pounds per foot. There's 2 of them on the bridge, and there's 4 beams. Okay. Future wearing surface, it's 25 pounds per square foot, applied over a roadway width of 34 feet, divided by 4 girders, so 0.213 kips per foot. Pretty familiar stuff by now, right? That should be pretty basic. Sound good? Okay. So, there's our dead loads, live loads. So we've got our truck and impact factors. Remember the impact, or truck, lane, and tandem, I guess I should say, and our impact factors. Remember, for fatigue, the impact factor is 1.15. For all the other limit states that we're going to consider, it's 1.33. Now, if you're doing portions of the deck, it ends up being 1.75, but we're not really worried about that. All right? Sound good? Okay. Now, we can't just take the live loads, put it on there, and say we're good, right? Because we got to use these wonderful things called live load distribution factors. So remember, we've got a whole host of equations. We've got our interior girder, and then we've got the exterior girder with the lever rule, the special analysis, all that stuff. So, how do we begin? Well, first off, we discussed multi-presence. Remember, multi-presence factors account for coincident truck loadings on a structure, right? So multi-presence factors, we have 1.2 for one lane loaded, 1.85, and then anything else past that we get 0.65. We have to apply those to the lever rule and to the special analysis provisions that we use for rigid cross-section rotation, okay? All right, so our longitudinal stiffness parameter, remember that's in calculations, that's our first step for live load distribution. So remember this formula, it's basically just a measure of your composite beam stiffness for distributions. So I plus AE squared, and then multiply all that times your modular ratio. You're basically transforming the whole thing into one big effective concrete beam, essentially is what you're trying to do. So we have our moment of inertia, the area, the EG squared. Notice these properties, like the moment of inertia, if I go back, I'm getting that here, you know, from all those section properties, right? It's not like I just came up with it. We used it, you know, so we got that here, All right? Sound good? All right. So, any questions? Okay. Now we can start computing distribution factors. So we have distribution factors for the interior girder for moment. So these equations should look fairly familiar, right? So girder spacing, span length, we have the longitudinal stiffness parameter, and our slab thickness, which ended up being 7.75 because we have an 8-inch slab and then a 1/4-inch integral wearing surface. So plug and chug, and there you go. Sound good? That's the interior girder for moment. Here's the interior girder for shear. Those equations are a little simpler, right? Of course, could have used that, right? The calcs, right? Fun stuff. All right. Exterior girders. Remember, the first thing we do is our lever rule analysis. So for the lever rule, we take that first truck, we set it 2 foot off the barrier, and then we assume this is a hinge. We say, all right, let's sum moments here to determine, all right, what's that reaction there got to be? We have 0.5 times this moment arm, which ends up being 9'9", plus 0.5 times this moment arm, which ends up being 3'9", or 3.75. Then we say, all right, what is the required reaction at 10'6", or 10.5 feet? So that reaction comes out to 643. Then we adjust that by multi-presence, all right, for one lane loaded. All right. Any questions? All right. Well, remember, that's the one lane loaded factor for moment and shear for the exterior girder. For multiple lanes loaded, we adjust our interior girder factor by correction. So for moment, it's 0.77 plus DE over 9.1. Remember, DE was the distance from essentially right there, from the edge of that parapet to the center of that girder, right? So that's where that 1.25 is coming from. So moment and shear is just a different correction factor. It's 0.6 plus DE over 10 for shear. There's our exterior girder distribution factors for moment and shear. Last one is special analysis, right? So that's where we treat the cross-section as if each of the girders were piles and our deck was our pile cap, and we're saying, okay, here's the truck. We don't want the whole thing to rotate, so what's the reaction got to be at that exterior girder? So I know the equation looks nasty, but it's just loads on pile groups. And if you had foundations, then this should be a pretty familiar topic. The equation might not look familiar, but you should be able to do the analysis pretty easily. So remember, you perform special analysis for the number of potential trucks or number of potential lanes on the bridge, okay? Now, let me go back a little bit. I should have had this image here. Okay, what's the total roadway width? It's 34 feet, right? So if I take 34 and I divide it by what, 12? Remember, that's how I determine the number of lanes. What is 34 into 12? It's 2.8 something. I don't round that up. It's 2 lanes. It's not 3, it's 2. I take the floor of that. So the integer portion. So going back to special analysis, I perform special analysis twice, okay? Number of lanes divided by number of beams plus the moment arm, which is from the center of the pattern of girders to the exterior most girder, which ends up being 15 feet 9 inches, or 15.75, times that moment arm plus that sum of x squared, right? Remember that sort of effective moment of inertia we calculated the girders. Do the same thing for 2 lanes loaded. The only thing that changes, the number of lanes becomes 2. We have to add up that second eccentricity, which does in fact end up being 0. And our multi-presence factor changes because now we've got 1, not 1.2. Sound good? Yes? Mm-hmm. Like if it was over here 1 foot, it'd be 12 minus 1 foot. If the truck ends up being over here. Because here's the idea, and that's a good question. So the idea is this. Imagine that like here's your bridge, okay? So we're treating the bridge as if this is a pile cap and there's piles going on down here, right? Make sense? When we do that first analysis, the idea is that the truck is somewhere over here and we're trying to determine how much load is on that last pile. Make sense? Now, let's sort of say that's the dividing line, that's the middle. If that second truck is like somewhere over here, it's going to add more load to that girder or that pile over here. But if I put the truck, let's say over there, well, that's going to lift the load off of it. Make sense? So that's why, yeah, do you just use a negative value? Yeah, because the truck being over here would sort of take the load off of that girder. So it'd be negative. Does that kind of make sense? Does that make sense to everybody else? That's an important point, and I really want to make sure that makes sense. Everybody okay with that? All right. All right. Last distribution factor we compute is for deflection. So we just take the maximum number of lanes, which is 2, divided by the number of beams. And if it's 2 lane loaded, the multi-presence factor is 1. There's your distribution factor for deflections. So when it's all said and done, you take the worst case for moment, the worst case for shear, and then the deflection value, and compute your moments. And that's basically it. So your worst case for moment, let me see, what do we got? Let me see if we can identify it. So moment, okay, 0.533, 0.766. That looks a little larger. I think it's this one right here. That's actually the worst case for moment, the 0.843. So that's going to be your controlling distribution factor for moment. For shear, I think it's actually one of the ones back here. Yeah, that's your worst case for shear, the 0.985. So, make sense? So you're just finding the worst one. So you can compute your dead load moments and shears, and then your live load moment and shear envelopes. So if you notice, like for the shear, there's a range of potential shears. Make sense? Theoretically, there's a range of potential live load moments as well. But because it's simply supported, they're all 0. Everybody okay with that? Any questions? Now it's time to use them, okay? Now we're going to start off with a newer check, which is this constructibility check. And I'm going to explain how this works, okay? So basically what we're doing is a deck casting analysis. And in a simply supported bridge in a deck casting analysis, what we're trying to do is this. Ultimately, we're trying to assess the condition of stresses as the concrete deck is being poured. Now, if you got a 60-foot, 80-foot creek crossing, how do you think they're going to pour the deck? They're just going to pour it in one big continuous pour. It's not like some, multi-span highway bridge where they pour the positive bending regions first and then come back and pour the negative bending regions. For this, they're just going to pour it in one fell swoop. So the wet concrete loads and all the non-composite loads, nudge, nudge, wink, wink, the DC1s, they have to be resisted by the steel beam by itself. Make sense? So we're going to have to assess that, but we're also going to have to assess that twisting effect. So we're going to have bending stresses, and we're going to have that lateral flange twisting effect. So we're going to have to assess both of them. Now, in this example, I'm going to throw in a couple values. First off, the unbraced length. That's going to be the cross frame spacing. I'm going to say that for this bridge, the cross frames are spaced at 20 feet, okay? Which that's a value I gave you for each of your projects. So some of you, you might have a 60-foot bridge, but the cross frames are every 30 feet or what have you. Okay. In addition, when you check constructibility, the web load shedding factor is always taken to be 1. So that's pretty simple. Because you're not allowed to, basically you're not allowed to shed any load off that section. It's got to resist the load all by itself. Now your RB is 1. Your hybrid girder factor RH is also 1 since we're dealing with a homogeneous shape. It's all 50 KSI. We don't have like a 50 KSI top flange and web, and then a 70 KSI bottom flange. We don't have to deal with that either. Sound good? Any questions? All right. Now, when you're doing a construction analysis, there's not just the wet concrete. There's also the other stuff that goes along with the analysis. So I'm going to propose the following load components. So the overhang deck forms, those are the brackets, the construction walkway, all that stuff. I'm going to assume that weighs 40 pounds per foot, okay? These are pretty reasonable estimates. You could obviously go through and look at your construction plans and actually do these takedowns. I'm not going to go crazy into load estimation because you all can do that. I mean, you all are smart enough now. And by the way, on your project, you're more than welcome to just use these values. This is totally fine, okay? We have the screed rail, which is the rail that the bidwell machine runs on. We have the railing as well, the walkway, and a lot of these loads, keep in mind, also take into account construction personnel as well. So some of this can get pretty hefty. If you've ever seen a construction bidwell, it's not a small machine. They're pretty large. Okay. The actual finishing machine itself, we're going to assume that to be 3,000 pounds. So it's funny how this is a point load, PL over 8, and these are all distributed loads, WL squared over 12. These are pretty reasonable values to go off of. Okay. Now, in order to do a constructability assessment, we have to calculate the capacity. That's where that whole 610.8 and Appendix A stuff came, that you're like, where the heck is this massive spreadsheet and all these crazy equations that we calculated? Where's this stuff coming from? Or where are we going to use it? Here's where we're going to use it, okay? Now, we ultimately will find that for this example, Appendix A is applicable. Now, how do we do that? A lot of this should be pretty familiar. So we start off, we've got our yield moments and our section moduli and all that. We've got our plastic moment. Remember that? And keep in mind, for this, we are looking only at the steel shape by itself. There's no concrete deck, no short-term composite or long-term composite. That doesn't exist because we're looking at the bridge as the concrete deck is being poured, right? The concrete is not effective at all in helping the girder resist those loads. So all we've got are PC, PW, and PT. We determine where the plastic neutral axis is and go off that table. Pretty straightforward stuff, right? You all should be able to do that, right? All right. We introduced these terms as well. Remember DC and D sub CP. So DC is the depth of the web in compression in the elastic range, and DCP is how much web is in compression at MP. And I'm not going to, belabor those calculations, but you can find them in here. For instance, we find that the P&A is in the web, and we get Y bar is 23.75. That is also how much of the web is in compression. Where am I getting DC? That's from the centroid, from all the section properties that we did way back in the beginning. So you all should know how to do that as well. Any questions? Okay. All right. We've got 3 checks to determine whether or not Appendix A is applicable. We have to use a yield stress less than 70 KSI. We have to meet the following web slenderness limit, and our IYC over IYT has to be greater than 0.3. Which we're good. Pretty basic stuff, right? So Appendix A is applicable. Remember, when in doubt, you want to use Appendix A. Appendix A the calculations might be more laborious, but in the end, it's more capacity, If you could just do more math and come up with a stronger girder, why not, Use it. It's what it's there for. So, if you have Appendix A governing for your section, you first compute your web classification factors, your RPCs. Since we're doing constructibility evaluation, I'm only looking at RPC. But remember, when we do RPC, remember there's that host of stuff that we had to compute, all those different properties, lambda RW and all of that. Go through and do all of this, and you will find that the web is non-compact, so you get to use your nice, pretty nasty equation that I'm sure you all loved, plugging and chugging, right? Your RPC and RPT, interpolation functions. Go through and chug it out, and you end up getting a web classification factor of about 1.15. You've got all the values, and you have calculators you can follow along if you'd like. Sound good? All right. Now, the last thing we need to do is actually use that to compute the capacity. It's a function of the flange compactness, and the flange for this section is in fact compact, so that actually did come out pretty easy. The moment capacity is just the yield moment times RPC. It's not a funky expression. Came out to be about 57.41 KSI. Okay. Remember, 610.8 allows you basically just to reach MY. So your maximum capacity could be 50 KSI. But Appendix A will allow you to go a little bit above and beyond. All right? Everybody okay so far? Okay, so this is where Appendix A comes from. We're calculating a flange capacity of 57.41 KSI. Now we got to compare that against load. Okay? Now remember, we've got two stresses we've got to assess. The regular old bending stresses that you get from a moment diagram, and then that twisting effect. Now we got the moment diagram. We looked at that earlier. Here's the twisting effect. Remember, FL squared over 12 and PL over 8. Pretty straightforward stuff. Now, we can use those expressions to compute the stresses very easily, okay? But then we've also got to do that second order check. Remember that whole backpack thing, right? The second order. We got to check that as well, okay? Now, if we end up meeting this limit, we don't have to deal with that second order stuff, that whole, kicking over and twisting thing. Okay, it's a pretty straightforward check. If your cross frame spacing is less than or equal to 1.2 times LP, that's one of those anchor points you did in Appendix A, times the following relationship, your moments divided by the yield moment on the bottom, on the top, C sub B, that moment gradient modifier for lateral torsional buckling, and then RB, which that's 1, because we're taking that to be 1 for this check. Pretty straightforward stuff. Now, we end up doing two different load combinations here. We do strength 1 and we do strength 4. The reason for doing strength 4 is strength 4 is indicative of very high dead to live load ratios. And think about it. When does a bridge see no dead or no live load but very high dead loads? During construction, right? There's no trucks on the bridge during construction. It's just the self-weight of the bridge itself. So strength 4 is a load combo that makes sense. We're only looking at DC1, so bear with me on that. Sound good? We got to compute C sub B, which I showed you all how to do that, and you all have the spreadsheet available that can do that. Remember, you interpolate your moments at the cross frames, and then in the middle, then plug and chug to get CB. Go through and do your calcs. When it's all said and done, you end up finding, shoot, we do have to do that backpack thing. We do have to do the second order analysis because it ends up, the limit doesn't quite meet. Cross frame spacing has to be less than or equal to what's calculated over here. Cross frame spacing is like 240 inches. We're nowhere near there. Shucks. We got to do a second order analysis. To do a second order analysis, what we end up doing is what's called an amplification. Think, standing on the hill with that backpack, those stresses build on themselves, right? And they amplify. And the easiest way to handle that is through what's called an amplification factor. We end up just taking the stresses that we straight calculate and amplifying them by this. Okay? So it's 0.85 divided by the following fraction. 1 minus your moments divided by F critical times your section modulus. Section modulus, that just comes straight from your section properties, that spreadsheet at the very beginning. And FCR is your elastic LTB stress. So again, I know more and more equations, but ultimately it's just very plug and chug. J, simple, right? H, remember H is from centroid of flange to centroid of flange, simple. That FCR term right here, it's just that. Now, if you took undergrad steel design, that should be a familiar equation, right? Elastic critical LTB stress. Pretty straightforward stuff. So far, so good. I know I'm throwing a lot of equations at you, but it's all done. Our hands aren't developing carpal tunnel writing it all out, right? Not too bad. Right. Okay. We're almost done, actually. So, here's the long and short of it. So, after you go through and do all those calculations, so your first order lateral torsional, or your first order lateral flange bending stresses, remember just lateral flange bending moments divided by your section modulus. Pretty straightforward. And I can show you all I'll produce probably a little guide I'll show you on MU Online to streamline that calc a little easier, because that's the one calc I think I'm skipping, but I can take those values and show you, oh, it's just, you'll see it's pretty plug and chug. Excuse me. Amplification factors. If here's your first order, here's your amplification, that times that, that's your second order. Here's your first order, amplification, that times that, there's your second order. Pretty simple. Excuse me. So here's your twisting stresses. This is your regular old simply supported beam, uniformly distributed. There's your bending. So here's bending stresses, here's twisting stresses. Lateral flange bending, if you will. So, pretty straightforward. We go through, we compute web bend buckling resistance, and once we've got that, which it ends up being just 50 KSI, we can start doing checks. We have 3 checks that we end up having to assess. We have just that the sum of those stresses better not be less than, or the sum of those stresses better be less than or equal to Fy. So we sum them up directly, and our worst case scenario ends up being strength 4, and we end up getting 35, well, about 36 KSI is how much is being put on the girder. That's less than it can hold, which is 50, so we're good. I know that's a pretty convoluted calculation, but figure we'll get that one out of the way first. Now you'll notice I've got these ratios, okay? These ratios, I'm just taking that divided by that. So that comes out to be about 0.72. I don't want that number to be greater than or equal to, or greater than 1. If it's greater than 1, that means there's more load on the system than there is resistance, and that's bad. That's grandma's in the river, okay? Now 0.99, that's great. I'd love them to be all 0.99. That's not going to happen, but if you can get one of them to be in that 0.9 range or something like that, you're doing pretty good. Sound good? Okay. Now this is your first check. Your second check involves the 1/3 rule. Remember, we look at that flange as if it's a beam column, and then that 1/3 rule is that interpolated effect for the top flange. This is where we use that value that took ages and ages to compute. So we compare our major axis bending and 1/3 of our twisting effect against that Appendix A massive calc. So here's the load, here's the resistance, we're good. I know it seemed like a crazy amount of math for one small little check, but it was necessary. Last thing we do, we compare our major axis bending against web buckling, and we're good there. So I know that was a lot of stuff for one small check. Any questions? Everybody good? Okay. Hang on with me a little bit, and I think we're not going to meet for round 2. We'll just go through this and then we'll call it. Sound good? Okay. So that's constructibility. That's the deck casting stuff that I said I would cover this week. The rest is review. Okay, the rest is review. All right. For the service limit state, we have 2 checks we're going to do. We're going to have live load deflection, and then we're going to have permanent deformations, the 95% of the yield stress. So live load deflection is pretty simple. You just, your limit is essentially L over 800, the length of the bridge divided by 800. That's the typical live load deflection limit for bridges that don't have sidewalks. And you can find that in section 2 of the spec. From the analysis, we just go through and do all those moment shears and deflections like we did before, and we find, well, 0.67. All right, we're good. That's it. And all we do to compute this value is this. We take the deflections from 2 cases, the truck, or 25% of the truck plus the lane. We apply the impact factor to the vehicular component, to the truck, and that's it. Worst case scenario, multiplied by your live load distribution factor. And that's it. Yes, sir? Because that's a good question. The reason why is, so first off, it goes into why we even do a live load deflection check in the first place. The reason why we do a live load deflection check is for user comfort. There is a perception that if the bridge deflects too much, that it's not going to be comfortable to drive on. Now, research has actually shown that that isn't valid. I honestly believe that the Canadians do a much better job for this check than we do. The Canadians, they do a live load deflection check, but they get their limit from the frequency of the bridge. Like did I bring up the example of the guitar in here? That if you play a guitar string, whether you play it really softly or you wail on it, you get the same note. Have I ever mentioned that to you all? Well, so I'll sort of go through that again. If you play a guitar, okay, and you take have you ever seen a guitar and played a guitar? Oh, okay, all right. If you take a guitar and you play a string very softly, or you wail on that string, okay, whether you wail on it or play it really softly, it's still the same note, right? Still the same tone. It's because all structures, once they're undergoing free vibration, vibrating on their own, they all vibrate at the same frequency, their own natural frequency. Okay, it's why the top string versus the string below it plays a different note. It's not, I mean, it's the same length, but the string itself is actually a different size. It's thinner, right? Notice how you go down, the guitar strings get thinner. That's why the guitar strings play different notes. Also, to bring up some pre-stress stuff, what do you have to do to a guitar every 2, 3, 4 weeks or what have you? You have to tune it. You have to tighten the guitar strings because guitar strings undergo relaxation. Remember, pre-stress loss, relaxation? So, there you go. But the Canadians, to get their L over 800 limit, they don't really use something as simple as L over 800. They actually relate it to its natural frequency. Because the idea is if you're on a bridge, the deflection is not what freaks you out and gives you discomfort. It's the bridge vibrating too much. I mean, if you've ever been on a large capacity highway bridge and the traffic stopped, and then on the other lane you've got these massive semis, you could feel the bridge vibrate a little bit sometimes. So there are bridges out there that pass L over 800 by a mile, but they still don't feel comfortable because of this. Now to go back really to your question, the idea is that if there is a sidewalk on the bridge, there's people on the bridge, so we're going to place a much more stringent limit on it. So convoluted answer, but I wanted to go into it a little bit. Does that answer your question though? Yeah. All right. Bye everybody else. Sound good? Okay. So yeah, ultimately the L over 800 limit is a bunch of junk. It came from a study done in the 30s on 6 railroad bridges. I'm not kidding. We apply it to every bridge in the United States because of 6 railroad bridges back in the 30s. So yeah, but that's just me. It's in spec. It's funny how it's listed as an optional check and then every state uses it. So I don't know. All right. That's your live load deflection check for service 2. If you recall, we ended up doing, remember our flange stresses? We had the top flange and the bottom flange based on your moments. Remember 1, 1, 1, and then that was 1.3. Remember we did all of that? We compute our flange stresses. So this is just bending moment sigma equals my over I. That's all this is, my over I. Why do I have the 12 there? Because I'm converting foot kips to inch kips. That's the reason why the 12's all over the place. Go through and I get a top flange stress of about 24 KSI and a bottom flange stress of 43 KSI. Notice we're talking about intact state, so I got to track the loads. This is DC1 on the non-composite section, DC2 and DW on long term, live load on short term. We got to go through and track it. All right, make sense? I compare those against 95% of the yield stress. I mean, obviously, that one's the worst case scenario. And this is, I mean, that's a pretty serious check on this bridge. We were like 90% of the way there. In fact, unless my memory is failing me, that's actually what governed the design. What was all said and done was that check. I mean, we wouldn't have known that until we went through and gone through the motions, but I think that's the one that actually governs. That's a pretty good ratio, you know what I mean? All right. That service, fatigue, okay? Fatigue, we're going to look at infinite life, so we're going to just assume, see, do we, no. I think we actually go through and determine whether we're in infinite life or finite life. But ultimately, infinite life governs. Our fatigue threshold stress is 12 KSI. We look at the traffic to determine whether or not we're in infinite life or finite life. For this one, we assume 4,000 trucks per day, which you go through and that's 4,000 trucks per day, not 4,000 vehicles per day. So that's 3,400 trucks in a single lane, and that's way more than the value for infinite life versus finite life. I think that was like 700 or 800 or something like that. So we are well within the wonderful world of infinite life. Calculate our stress range at midspan. Our actual stresses are 10.6. This is the capacity. We're good, 0.883. The last and final check that we need to do is the strength limit state, where we're looking at whether or not the bridge is going to fall down or not. Okay. So for flexural capacity, we've got to look at MP again, but in this case, we're looking at MP for the entire girder and the slab. So plug and chug, we get that the plastic neutral axis is in the top flange. Go through and we get an MP of about 5,400 foot kips. We need to determine phi mn. So we need to determine whether or not it's compact or not, which it ends up being that because our web slenderness is good. Our flange yield stress is less than 70. And we meet that limit easily since DCP is 0. We get our capacity, remember that bilinear fit, it was either MP or that linear trend off of MP. Go through and we get an actual moment capacity of about 5,031 foot kips. Compare that against the applied moments. Nope, I was wrong, that's the one that governed, 0.928. So far so good, right? Now, you're going to like the shear check on this girder because it's pretty simple. All right? Remember that massive shear stiffener layout that we did? Remember that? Well, to compute the capacity of the web and shear and to see whether or not we even need stiffeners, what we end up doing is this. We assume, first off, that there's no stiffeners on the girder at all. Then we say, all right, let's determine what's the capacity of the web if there are no stiffeners. Let's compare that against the loads and see, well, do we even need them? Let's go through and do that. We compute the plastic force on the web in shear. Remember, that's 0.58 times the plastic force, Fy times the area. Remember, we use that 0.58 for that von Mises yield criterion for the metal. You know, remember, metals in shear yield at about 58% of the yield stress. We're then going to take that and multiply it by C. That's that constant that'll tell us how the web buckles. So we end up checking our web slenderness to see what limit we're in. I think we're in zone 2. So our C constant is computed as follows. I mean, you can go through and find all the equations in the shear presentation. They're pretty simple. And lo and behold, we get a shear capacity of about 437 kips. Now that's assuming there's no stiffeners whatsoever at all on the girder. The loads are only about 271. So that means, you know what? We don't need to throw any stiffeners on there at all. No, we don't have to do that massive stiffener layout like we did on that last example. That one example, I mean, that was a really slender girder over a very long span. Yeah, you needed some stiffeners. This is an 80-foot or creek crossing. You shouldn't need any if done properly, and you didn't. Sound good? The last check is just a ductility check. It's just comparing dP and dt, which you all have. We have that from this, from doing the moment check. It's pretty basic. Right here. So dP's 8.94 inches. The total depth of the section was 43, so we're good. Now, we just went through a lot of stuff just now, right? A lot of different calcs, a lot of different math. It probably seemed like a whirlwind, right? Imagine if we had done this in week 1. You know what I mean? Where you didn't know what any of those terms were. I'd be on this presentation for, well, the whole semester, because that's what we did all semester. Was really, I know it sounds silly, but we were trying to explain that. Everything that went along in that presentation, that's what we were trying to explain. What I'm looking for in your final project is that, okay? This is a table that is the, hey, here it is, everything we just computed. So what I did is I listed, here's the limit states, like for instance, for fatigue, see that? That's that ratio that we calculated, the load over the resistance, the load over the resistance. And that, right there, that's all you need to know for the design. For instance, for strength, for moment, the performance ratio was 0.928. So that tells us that we were good and we were efficient, okay? If your largest performance ratio is over 0.9, you're doing good. That's a good, efficient design. You are going to have, I mean, let's just be frank, you're going to have some of them that are like 0.5, and like you're going to look at this limit, this live load deflection, and you're thinking, goodness gracious, we could have done a better job than that. Yeah, but as soon as you start tweaking dimensions, you're going to change this, you know? So not all of them are going to be 1s. You know, I'd love them for it to be, but that doesn't exist, okay? But the worst case scenario should be somewhat close to 1, okay? Any questions? Ultimately, what I'm going to look for when I check your project is I want to see the dimensions of the girder, and I want to see what's going on here. And that's it. That's the long and short of it. Before we close it out for the day, does anybody have any questions at all about the project, about any of these calculations? I know we went through a lot of stuff, but in that handout is a simple container, hey, here it is, for a given bridge, start to finish. And I know that there's a lot of stuff that took a lot of explanation. That's what this whole semester was about, you know what I mean? Now you can engineer a bridge from start to finish, and that's sort of the whole point. So. No, that's what's in the spreadsheet. If you look on the, okay, that's a good question. If you look on Blackboard, let me see if I can log in. I hope I put that on there. It is 7:57 p.m. All right. Okay, so if you look right here for loads and parameters for your project, so I'm in course content. Okay, I'm going to pull up this right here, this Excel sheet. And I'll change that to December 16th. It's not due just on Friday. So, okay. These are the project options, right? So remember we had our little random drawing. Somebody got option 8, somebody got option 3, what have you. For instance, if you go to dead loads, all you have to do is enter in, a girder space or a span length. So for instance, if I say, well, I got the 90-foot bridge. Oh, enable editing. If I say I've got the 90-foot bridge, everything else updates. You know what I mean? Now you're going to have to compute DC1 and DC2 and DW, but the idea is you can link, your previous calculations. You just say equals whatever, and it'll do that. For live loads, all you have to do is enter in your span length. So for instance, if it's 70, there you go. And what it's doing is there's I think it's like right here, there's a hidden sheet that's got everything listed for every span length. So I decided to make it easy on you, and if you've got a 50-foot bridge, all your moments, shears, and deflections are taken care of. So that's one thing. That's a computer. That's what a computer's for. You did an influence line homework. That's just influence lines over and over again, and you've got a bachelor's degree, so I know you can do that. But everything else, the section properties, the flexural calcs, the shear calcs, that you do need to do. But I wanted to give you the raw data so that you all can take it and use it as appropriate. So, and if you go to the grade column or the grade section of grades in Blackboard, there's a column that's called Project ID, in case you forgot. So it's got, like you might have Project ID 4 or what have you. That's your parameters. So, sound good? All right. Any other questions at all on bridge engineering, life? Yeah. Anything at all? All right. Well, look, I know that this was a marathon lecture tonight, but I thought this was a good way to close it out because that's it. That's in a nutshell. That is how to design a bridge. All I can say about concrete, if you are using a concrete bridge, really the only thing that changes is your resistance. I mean, the loads are the same. It's still the same truck and whatnot. It's just different resistance. But that's what pre-stress is for. Take pre-stress. You'll learn all about it. All right. That's not only all I have for you for tonight. That's it. That's all we've got. I will email you the final. It'll be a short answer discussion-based final. You all have your project that you're working on. Both of them due next Friday on the 16th at 5 o'clock. With that being said, it's been fun. It's been a marathon, but we've gotten through some good stuff. If you all ever need anything at all, don't hesitate to contact me. That's all I got. I will leave you all to it. You all have a good evening.